take control.
Okay, so our senior design project was the solar panel controller for Dr. Michael Baswell. My name is Dylan Schultz.
I'm Dustin Morris.
I'm James Singleton.
Brady Allred.
Flash Patel. So the goal of our project was to build a solar controller for a standard off-grid home. It will regulate the battery voltage provided by a 6 solar panel array. It also has the ability to control the water pumping to 2 tanks, and it has an excess power bus. The main control unit we went with was the Arduino Mega 2560. So there are multiple ways to control solar arrays. The first is maximum power point tracking, which simply just keeps the panels at their maximum power output. Another method is pulse width modulation, which sends a PWM signal to a transistor that regulates the current from the panel to the battery. The third method is relay method. It allows for the control of high voltage, high current panels individually, and it can be controlled with a microcontroller. So we decided to go with the relay method because of its simple control. We can take a panel in and out of the battery circuit individually. They consume low power. When the relay is in its normally open state, when the relay is active, it consumes about 0.2 amps. When it's normally closed, it consumes about 0.02 amps. And it was customer preference due to replacement upon failure. So if the relay were to fail, you can just take out one relay versus a whole array. And in the off state, they allow us to send the panel somewhere else, to send the power from the panel somewhere else when it's not going to the battery. We also decided to go with current control versus voltage control. So when we started the first semester, we were given the Tamura LO8P, which is a Hall effect current sensor. It allows the wire to remain uncut since it will pass through an aperture in the device, but it requires a positive and negative 12 volts, which we struggled to provide the negative 12 in our box in a simple manner. It also had a range of plus and minus 100 amps, which is outside of the typical 10 amp output of our panels, so that caused our resolution to go down. So we decided to go with the ACS 712, which is also a Hall effect, but you have to cut the wire, which wasn't ideal, but it was a simple installation, and it's Arduino compatible. It also has a better range of plus and minus 20 amps, which helps the resolution out quite a bit.
As Dylan was saying earlier, we designed our entire box to be modular. This means that any component in our box is laid out and mounted in such a way that if you need to remove it because it went bad, you can just unscrew it and pull it out and replace it. Once we had a general layout for the box, we designed wires to fit it. We sized the wires in a way that the gauges were based on the power consumption of each piece. We also labeled each wire color-coded so that you can look at a wire and know exactly if it's a signal wire, power wire, and exactly what kind of signal or power it's holding. We also put 6 switches on the outside of the box. One switch controls the power for the LCD. One switch will clear errors that pop up in our code. One switch is a manual control switch for our tanks in case the user wants to manually pump each one individually. And then one switch will equalize the battery. We've also got 2 switches left over that can be used by the user for anything they deem necessary. All 6 switches are ground control. Our control unit is very difficult to test in the field just because we'd have to take it out there, bring it back. So in order to test it here, we built a simulator. The simulator we just hook up to the box, and since we have 6 panels, we have 6 LEDs on the left side of the box. And when the relays are in the open position, the corresponding LED for that panel is no longer lit, so we know exactly which panels are on when they should be. We've also got switches on our box that simulate the sensors on the water tanks. We've got 2 top sensors, a middle sensor, and a low sensor. This way we can simulate how high the water is in the tank. The entire simulator is powered by 2 power supplies. One is set to 35 volts. The other you vary from 20 to 30 volts. The 20 to 30 volts simulates the battery voltage. The 35 volt just creates a potential difference for the LEDs to turn on.
For our project, we chose the Arduino microcontroller based on an Atmel microprocessor. We chose it mainly for its large number of analog inputs, and it has plenty of digital inputs and outputs for us to use for controlling the various things in the box. For programming and editing the code, programming the microcontroller and editing the code, we use the Arduino IDE. It uses a subset of the C++ language and has excellent documentation. As far as our main algorithm is concerned, as mentioned before, it controls the 6 solar panels and whether or not they're connected to the battery by using relays. It regulates the battery voltage by either adding a panel if the battery is too low or removing a panel if the battery is too high. We also, as mentioned before, control a solenoid and a pump in order to control the water level in a couple of water tanks. And the target water level in those tanks is dependent on the battery charge state. If the battery is full, then we can go ahead and pump and fill both tanks. If the battery is discharged, then we don't want to damage the battery, so we only pump to half full. In order to follow good programming practice, we put constants in a bunch of constants at the beginning of our code so that we can easily change various parameters, and there are a number of helper functions to help with the organization of the code. While it does this, our code also performs error checking. This is an example of trying to find an error. In this example, we're trying to find out if one of our solar panels is underproducing, producing less than the others. Here we have panels 1 and 2 are on, the rest of them are deactivated, so the values are ignored. The values are in CT1 and CT2, where CT stands for current transducer. We first adjust for their 2.5 volt offset, and then we find the average among the active panels. Then we find the difference between the average and the adjusted values. And if this difference is beyond a tolerance, then we can say this panel is underproducing. It is below too much from the average of the other producing panels. Then we increment a downtime counter, and if a panel has too much consecutive downtime, which is also controlled by that threshold is another constant in the code, then we can throw an error and say this panel maybe has a leaf on it, maybe it's broken, but it's been down as compared to the other panels way too long. And Raj will tell us what we do once we detect an error.
After the error has been detected by the microcontroller, it assigns a 2-digit error code predetermined by us and stored in the microcontroller's memory. After it assigns the code to that error, it passes that code to the LCD to be displayed for the user, saying that there is an error in the system, as well as a data logs it on the SD card with an understand. After it has passed the error to the LCD, the user can switch the LCD on-off switch and see the error and refer to a user manual to see a step-by-step instruction on how to fix the error. The LCD's main purpose is to show error codes and to show system status if there are no errors. The LCD has 20 lines, 20 characters per line. It has a total of 4 lines, and it uses an I2C backpack, which reduces the number of pins versus using a parallel serial communication. And as James mentioned before, the LCD uses a ground control, which will reduce power instead of just keeping it all the time, as well as the clear error codes. When the error has been seen by the user, they can throw that switch and clear the error from the microcontroller memory. For the data logging purposes, we use a SD card shield, micro SD card shield designed by Cadillac, and it's designed for Arduino itself. The shield uses the SPI channel on the microcontroller, and every minute we data log time, battery voltage, the panels that are currently on, the panels that are weren't on, the current from each of the 6 CTs, and the error codes. The reason why we chose these parameters is because with the time and the battery voltage, you can see the demand profile of the user throughout the day, and with the current from the CT, you can see what time of the day the panels are placed in the maximum power.
So, Raj mentioned we have a user manual. So thinking forward that if this project were ever to be put into actual production, you would need a user manual for it. So we gave a basic overview of the controller, getting to know your solar controller. And it comes complete with the device layout and electrical schematics so that you can see where the components fall on the board if you don't know what they actually are. And it shows the electrical connection in between them, that way you can rewire them. It also comes complete with an error table, as Raj mentioned. So the predetermined error codes that show up on the LCD appear in the manual, as well as a brief description of what is wrong with the system. You can go down below it and see the device repair and replacement steps. And it also comes with a component list and the specifications, so that if you run out of spare parts, you can go on eBay or Amazon or to your local hardware store and buy a component that has the exact same specifications as what you took out, even though it's not the same brand.
So looking to the further development of our project, we feel like we've done the adequate work to make our project perform at the best of its ability. So first thing we want to look at, how could we improve our system? First one is the physical build. With having the actual size of the controller, the customer we're working with in Dr. Baswell, the space is really limited to what we can actually use. So we know that going further into applications with other clients, we may actually run into situations with a smaller area. So we want to look at maybe decreasing the size. Some of our relays, we could put them closer. We have a lot of wasted space in channeling with the leaving spaces for the wires and stuff. We could actually cut that down a little bit. The next thing we want to look into is a smaller, more efficient and reliable controller. So we chose the Arduino, like Dustin said, because we needed the inputs and outputs, we needed the analog pins and stuff, but a lot of those pins are unused. So we could actually try to tailor a microcontroller more to our needs and have less unused pins. Again, the Arduino is not really commercial grade. It's not specified to be industrial grade, so we would like to find something to be more reliable in that sense. So the next thing is the code structure. As you can see here, the big data. It's a big thing with today's industry is pulling AMI data, pulling SCADA data, and looking exactly how the system is operating due to its load. So if we were to take that, as Raj mentioned earlier, we could take the customer, if we were to install it on his house, given more time, we would have been able to let it run for a few weeks or a month and build his load profile. So as you see down here, this is like a single household's load profile. You have a lot of peaks and a lot of valleys. We could try our best to try to alleviate peaks and valleys. The way of doing that, for example, might be in the morning. So in the morning, you all wake up and you're all getting ready at the same time. Well, if you want your water to come on and be heating your water when you wake up, so you have a good hot shower, we might be able to move that back a little bit, given some testing, because your water tank might hold some hot water for longer, and try to smooth that out so you're not having all your load in the morning. Vice versa in the afternoons, you come home, your air conditioning kicks on. You could actually move that forward a little bit, have it kick on, get your house cool before you get there, and the whole load comes back in to try to smooth this out a little bit. So the last thing would be better error and failure protection. With our CTs and with our panels, Dustin mentioned this earlier, we could actually go out to the panels, install this onto the user's house, and actually lay like cardboard or something on top of the panel and see how the panel reacts and know exactly whenever it's fully covered, what does it actually output? Does it output 0? We're not really sure what it would do, but that would help us make a better prediction of the life of that panel to see what actually is going on with it. Same thing for the CTs. We're not really sure when they go to fail. We've not had it installed long enough to see what would happen if it failed. Does it actually output 0? Does it output a value close to 0? So we could actually do more testing to see what would actually happen, and we could predict better instead of just doing an average over all the CTs, or we could actually hone in the software to make a better prediction about the system. So here's our division of labor. This is all of what we've done. We've basically had our hands in on everything at any given point, so we feel like we've all put in adequate work to get the project done and make it to the best of our abilities. Thank you, and are there any questions?
The enclosure you used, that's intended to be used indoors, undercover, because you have the switches and.
Yes. It actually, the box has a seal when it closes, and it's actually like watertight, but on the bottom, the seal, we didn't put the seal on the bottom because we wanted it to be able to, if like anything got in there, to drain out, to leak out, yes.
And you've got the switches coming out the side, which I don't know how good a seal you have on that.
We're actually going to put silicone epoxy around it, try to keep like bugs and stuff out, but that's what we'll do before we install it to the customer's house.
So I'm sure Dr. Johnson would field trial this for you out of his place. I'm suspecting that this may have been done as for Dr. Johnson's place. So I think it's a great opportunity to give it a shot.
So one question, you mentioned that you can power goes to the battery, or it can go to pumping. But what if you get excess power and you don't need to pump and the batteries are full? Where are you? What are you doing with it?
So the excess power when the relay is normally, if we sit it normally closed, that way we don't waste power keeping the relay on when we're trying to charge the battery. So the relays are thrown when there's too much power on the battery, and they go to this bar down here. If you can see it, it comes out to this lug. So this lug can be attached to anything the user wants. Hot water heater, air conditioning unit, it's completely user defined.
You turn something on randomly when you have power to run it with.
It would be wasted.
Or you turn it off.
Okay.
The MET department is working on a hot water heater, and it's gonna have like 12 elements in it, and this can plug into that. So none of the energy will be wasted. It'll be
Heating water.
You mentioned the power consumption of the relays and two positions. What were the numbers again?
So when the relay sits at its normally closed state, when there's no control from the Arduino, it uses around 0.02 amps, just cycling through it. And then when we open the relay and send it to the excess power bus, it uses around 0.2 amps.
It's not a latching relay.
You have to consistently send power to it.
So how are you driving the relays?
We've got power coming from our 12 or 24 volt bus, which goes to, down here we've got a 5 volt power supply, where it transforms the 24 volt to 5 volt, and then we've just got 5 volts running to the relays.
For power, for control, the Arduino pin goes to a optical isolator that is on these circuit boards, and there is a transistor circuit. I'm assuming there'd have to be, but you can see that there is an opto isolator on it. So that allows the Arduino to be more fully isolated from the control system, from the main
So,
power
okay, so it's not just a relay, it's a whole little control board.
Right. Yes, sir. All we have to do is put in a 0 to 5 volt signal, and then the electronics on the relay module handle the relay.
And like in your example where you take panel 2 offline, panel 3 then become panel 2.
No, they have consistent numbers.
Like we've got R6, 5, 4, 3, 2, 1, corresponding to the panel inputs 1 through 6.
So I mean, you just use panel 3 instead of panel 2.
Usually we'll turn them, they turn on, one will turn on first, and then they go in order. So if 6 is on, 5 through 1 are also on, always. If 4 is on, 3, 2, 1 are always on, but 5 and 6 could be off.
Well,
So if you get an error on 2, then you can just skip over 2
Yes.
and go to
It'll just, it looks at the array and then just adds 1 or takes away 1, and if one relay is stuck or panel's not producing, it'll just add another based on the thresholds. Something that we would have liked to have done would be to modify the algorithm so that we have wear leveling like you have in solid state drives, to where you don't have all your load on switching on this one and this, because this means this relay will be doing more switching than that one. So it would be nice if we could do a more random or even out the wear so that they don't consistently have to replace these relays.
so what's your total power consumption of, like, in the worst case scenario, you're turning on all the relays and you've got everything powered up?
Worst case scenario should be around 3 amps at the absolute max. Usually if they're all on, it should be closer to around 2.5.
But that means the batteries are completely filled
Yes.
and topped off, so.
They only start turning the relays off, sending power to them, when you have a high battery voltage to begin with.
Okay. So they're normally closed.
Yes.
Did you say what the cost was and I missed it?
No.
We were not given a cost constraint. We were just, as Dr. Baswell needed stuff or we needed stuff in, we just, asked him for things. But we were not given like cost constraints or a budget on this.
So do you know what it cost, or
We didn't purchase anything.
To it because you weren't, that wasn't one of the constraints?
We just used stuff that was in the lab or that he would order for us from the lab.
It was around.
Yeah, I'd like to have a project like that.
I've had a lot of projects like that where I had no budget, go find, but you gotta find something here.
Open Texas project, that's what I want.
It shows up and magically requested, get used to it. That's the last time in your life.
So,
Ready for the real world.
yeah, so you're using the current to charge batteries until you no longer need batteries charged, right? So you're turning off, solar panels, just disabling them?
They just,
Yes.
it just gets sent from where it normally goes to here, and it gets sent to the battery.
Yeah.
Instead, it gets sent right here.
Yeah, and if there's no consumer of that, is that a problem for the solar panels to
No.
just build up a charge?
There's no load. So if there's no load, there's not going to be a draw on it. So essentially, we look at it as that power's going to be wasted anyways. It's just going to sit there on a lug. It wasn't being used.
Well, the sun's gonna
So might as
shine.
well put it there. And if a chance a load might come on, it could be utilized instead of using the batteries.
And the output voltage on that lug is what?
24 volts.
No.
Nope.
Yeah, 24 volts. Not
Yes.
okay.
Nominal 24.
Just need more batteries, that's, excess capacity.
Yeah, that actually is a good point. If you're getting a lot of excess capacity, it'd be nice to have an indicator saying, hey, it's going to need a lot. Add some more batteries. You can add some more batteries if you want to.
Well, the goal of this project was actually to reduce the amount of batteries that you need. Because you can pump water during full battery time instead of whenever you need the water. Pop off the tanks. Other things, this is going in my house, so I've got a circuit. that
Oh,
runs
okay.
along.
Now, Dr. Johnson's broken your house. Okay.
This
Now,
is there's a circuit that runs all through the house.
could you build a second one for Dr. Johnson?
Rechargeables can be plugged in, like laptops and other things. And in the middle of the day, when the batteries are full, that circuit comes on, and everything that I've got that recharges can be charged up. Other things, I finance these projects sometimes, but I want to have a freezer made where you freeze a substance, an alcohol water substance or something like that, at 0 degrees during the day, and then that can keep the freezer on, keep the food frozen at night, saving the battery. So you don't need but a little battery, but you need quite a few panels, it seems like. It saves on the battery, so the battery lifetime lasts longer. That's my goal. Save the battery.
Yes, but not like to hear that. Any other questions? Thank you very much, guys.
Thank you all.
Yeah, you will. Drive safely.
So